That's going great. All righty. All right, so we're going to now. So I hope you guys know this is College Physics 1, so you're all in the right place. All right, so pretty much we're going to start off with vectors, right? Because vectors are pretty much everything you do in physics. Everything's going to relate back to vectors some way, some shape. You see it in forces. You're going to see it in kinematics. You're going to see it in energy. You're going to see it in rotational. Everything will relate back to vectors. And so knowing how to add and subtract them wherever they are is very crucial into your understanding of physics, right? So, all right. So there's two main ways of adding vectors, right? So you have what's called the easy way, right? The tail to tail, or tail to head, where you have two vectors in the same position in the same direction, right? And so if you have a vector like that, all right, can you guys see that clearly? How do you mess with that? All right. So it just turns out to be simple addition, right? So 5 plus 5 equals 10. And if they're in opposite directions, right, you subtract. So that's the easy way. Everyone gets that, right? I hope. All right. So then the other way is when they are pretty much head to tail, but they make a 90-degree angle. So they have to be perpendicular to use this way, right? So either you have a vector that's going straight up, and one straight to the right, so you have the right angle. And you use Pythagorean to solve that, right? So you're just going to use a squared plus b squared equals c squared. And that will solve for the combined vector. So if you were to have the same two vectors from before, 5 and 5, you just do 25 plus 25 equals 50. And the square root of 50 would be the total vector. So those are the only two ways you can add that. And you cannot add vectors any other way. So there's going to be situations where they're going to give you vectors that aren't perpendicular and they aren't like in the same direction. So what do? We have to use trig, right? So we might have a graph, right, where one is on the x-axis perfectly with the magnitude of 10, but the other one is at a 30-degree angle with the same magnitude of 10. So the one that is usually this way, the one that's already on an with the x or parallel to y, you're going to leave that alone. You're the one. So you're going to break the theta up into two parts. You're going to break so we're going to rewrite this over here. This magnitude of 10 with a theta of 30 degrees, you're going to break it up into a y and then an x. And so the rule of thumb is that x is associated with the trig function of cosine, and y is associated with the trig function of sine. And that rule works 9 out of 10 times. So if you want to memorize it that way, instead of having to do SOHCAHTOA every time, that works. There's only one exception, which we'll get later on in the session, which is inclined planes. Okay? So we break that up and we do, the x would be 10 cosine 30 degrees equals the vector on the x-axis, and then 10 sine 30 degrees equals the vector on the y. Okay. So I'm just going to pull out a calculator here, right? You guys have calculators, so like if I can just call on you to make it faster? All right, so we get 10 cosine 30. Yeah. For now, does anybody have that? Because I have to switch my calculator. Give me 10. 8.6. All right, so 8.7. And did anyone solve for the sine? 5? All right, so 5. So now we have it divided in, so if we were to redraw our new vectors, we now have a vector on the y perfectly with the magnitude of 5, the original vector on the x with a 10, plus the component vector that we solved for on the x with an 8.7, right? So just like we did with this first one, we can just add them simply. So 10 plus 8.7 is going to give us an x of 18.7. Oh, sorry. Thank you, Shanley. Right? 18.7 with the vertical vector of 5, right? And then now we just have a perpendicular vector, and we can just add it using Pythagorean. 5 squared plus 18.7 squared will give us c squared, and c is equal to, anybody work that? All right, 19.4. And so that would be your combined vector. So that's how you would add these vectors here to get your combined vector of 19.4. Now, there's two components of every vector, right? So if you know them, we know our answer isn't complete yet. You have the magnitude and the direction. So how you solve for the direction is we use an inverse trig function, right? And my rule of thumb for this is the inverse. You can use any inverse function. You can use arc cosine, arc sine, and arc tangent. I would use the inverse function that uses the two sides that were given to you, because usually a physics problem will give you like information, and you can use those two ones to solve for the arc. So let me show you what I'm talking about, right? So we solved for 5 and 18.7. Our combined vector would be the 19.4. Can you guys see that? All right. So we can use tan, which is opposite over adjacent. So 5 over 18.7 is our ratio. And then we use the inverse trig function of tan, and that will give us theta. All right? And so you get, you would get like 14.9, right? So that would be your direction, 14.9 degrees. And so that's everything vectors has to go. So vectors at its face value is not too complex. You just have to remember to use them, because right here it looks easy and straightforward, but it's not going to tell you this is a vector. You just need to understand that you have given vectors. So acceleration, velocity, displacement, these are all vectors. So these same principles apply to them as well. All right. So any thoughts, concerns, questions about that? No? All right. Okay. All right, so the next thing you guys learned after that, well, not for everyone because a lot of the professors did different orders, but the main thing is kinematics, right? And kinematics is any problem that's asking you to solve or it goes. So these problems work out to be very plug and chug. They work out in the simple pattern of you're given information, you plug in that information into your formulas, you solve for one variable, you use that variable to solve for what was asked for in the question, right? And so those formulas work out to be these following. X equals velocity initial times time plus 1/2 acceleration times time squared. V final equals V initial plus AT, and then V final squared equals V initial squared plus 2AX. For what I've heard, you guys don't need to worry yourselves about memorizing these formulas because a formula sheet will be given to you. So these are formulas that will be on the formula sheet, okay? And then there's simple formulas that are really helpful in situations where acceleration is 0. So these are the formulas you can use when acceleration is 0 to save yourself some effort. You see that? All right. So x equals vt. And pretty much any variation of that formula you can use. So like if you want to solve for time, you can do x divided by v equals t, and so on. You just manipulate it algebraically. All right? So let's see an example of that problem at work. So a very common question for one-directional kinematics, because we're only going to be dealing with one axis, whether it's in the y or the x. If there's only one axis, it's one-directional. And so a very common problem like that would be something along the lines, usually dealing with cars or collisions, things like that. So you have a car, right? And it's traveling with an initial velocity of 20 meters per second. An obstruction occurs down the road 15 meters away, right? It'll give you the information that these cars have a brake with an acceleration speed of negative 2.5 meters per second squared, right? And so it'll ask you, does this car stop in time or does it get into a car accident, right? So I did this for you guys in this one. A really good strategy, even if you don't think it would work, is to draw a picture. Read the question, pull the information out, and draw pictures, right? So as you can see, you have all your information here written for you, and from there on, you just need to plug in for what's missing, right? So we write our list of variables. So we have initial velocity is 20 meters per second. Our final velocity is going to be 0 meters per second because we're coming to a stop. Our acceleration is given to us as negative 2.5 meters per second squared. Our x, now this is where it gets a little confusing. Anybody here think x should be 50? Well, very good. Yeah. 50 is our point of comparison. So sometimes you need to understand the difference between the question giving you a variable or giving you a point of comparison. In this question, it doesn't tell us that the car takes 50 meters to stop. It says that that there's 50 meters available to make the stop safely. So we are trying to solve how far does it take to stop. And then we're going to use that to compare it to the 50 to answer the question whether we get into a car accident or not. So, and then time is not known. So we use our variables listed here, and we look at the formulas given, and we find what can we solve for. So here we have x equals initial velocity times time plus. Looks good, it solves for what we need, but the thing is, so what we data into a different formula to solve for time, so then we can solve for x, right? So here we have the initial velocity, we have the acceleration, and we have the final, so we can solve for the time. So we're going to do that. So our final velocity is 0 meters per second. And our initial velocity is 20 meters per second. Plus our acceleration of negative 2.5 meters per second squared times time, right? So if we do algebra, we subtract the 20, and then we divide by the acceleration to isolate time. And we get time to be 8 seconds, right? And now we're just going to plug into the first formula where x is equal to our initial velocity of 20 meters per second plus our 1/2 times our acceleration of negative 2.5 times our time of 8 seconds squared. And x will equal what?
You do velocity times time. X equals velocity times time.
Wait, what, Chandler?
Or your equation is x equals 20 meters per second times
Yeah.
time.
Oh, yeah, yeah. Thanks. Good catch. Good catch. Yeah, there's a time here. So that's 8. So we get 2.5 times 64. And so we get a distance of 80 meters. So we don't stop time. So not there. Like solving for one, and because that's usually how. But keep your eyes open for like the formulas, because again, if you have all the given information, you can plug it in. Go for it, because if it saves you an extra step, time is money, you know? All right, so that's 1D directional. All right, so that's the math as far as one-directional kinematics. Now we move on to the conceptual stuff, right? So some people find the conceptual stuff a little more difficult, but it doesn't have to be, right? So usually how conceptual and three main variables that are usually used in graphs as far as the conceptual stuff goes. We have displacement, velocity, and acceleration, and all of them are compared over time. So we're going to have to make assumptions based off the other graphs. So if you're given this graph, x over time, right? And you have the graph that shows this. Very often you'll be asked to give the corresponding graphs of velocity over time and acceleration over time. So how you approach these questions is you look at the graph and you try to make a story about it. Like, what is this graph telling me, right? So we have a displacement that is constantly increasing, right? So that could be a guy walking at a constant speed. So if this guy is walking at a constant speed, we can see that the slope is constant, our displacement is constant. So he's moving at a constant speed, so that our velocity is going to be constant, right? And then if velocity is constant, are we speeding up or slowing down? Is the next question you ask yourself. And if it's constant, no, we're not. We're at the same speed. So acceleration is just going to be 0. I know this is physics, but has anybody here taken calculus? Right, so you guys just understand that the slope of one graph is going to be the plot of the next one, so it's just the derivative of each other. That's how it works out. So if that definition makes more sense to you, feel free to apply it. But again, you can still just go ahead and logic your way through it. So another one, just for good practice, you might be given the acceleration graph and be asked to work backwards. So if acceleration is constant, we know that velocity is constantly increasing. And since acceleration is on the positive y, we know that velocity is positively increasing constantly. And if velocity is constantly increasing, we know our speed is constantly increasing. And with each unit of time, we're covering more and more distance per unit of time, which would result in displacement being an exponential, right? And then going back to the derivative, you take the derivative of the displacement, you'd get the velocity, and the derivative of velocity would give you acceleration. So that is the conceptual stuff. All right, so now we move up to one step a little more complex, right? Build on itself. So as you see, you'll learn something and it'll build up. So we go from vectors to 1D to 2D, and then it resets. So the climax of this would be 2D kinematics, right? And so two-directional, we saw the car. So fraud. It'd be said. And so how you approach these problems is you need to understand a couple of concepts. The first concept to understand is that x and y are independent. So whatever you do, take a value that you solved for on the x and assume that it's the same on the y, because that will be wrong. There's only one exception to that rule, and that is time, right? Time is temporal. It transcends. So it will be on both sides. And another way to think about that is that if you throw a ball, it hits the floor, right? That motion is going to be stopped. Regardless if it goes horizontal or y, it's stopped moving. So that's why the time will be the same. So let's see that. Right? So a good way to divide and organize your work on these problems is to write an x and a y t-chart, right? So then we can have our variables for the x and the y separately and in a very readily available position to do the math with. So an example problem could be something along the lines of a soccer ball is kicked with a theta of 30 degrees at 15 meters per second, right? I want to know the maximum height and how far it goes, which is the range, right? All right, so again, column. So on the y-axis, acceleration that is an acceleration that is always present. Is happening. This is what you're going to. It's going to be negative 9.8 on the y. All right. While on the x-axis, unless something push, and then it's just free flying. So acceleration is going to be 0. Those are two. If it says otherwise. All right. So then we have to find our y and our x, right? For the initial velocities. And the way to do that is we have to go back to vectors. So we know velocity is a vector. So if we have a velocity of 15 meters per second with a degree of 30 degrees, we can use our trig functions to solve for the y component and the x component of velocity. So x, again, is associated with cosine. So you take the magnitude times cosine 30 degrees. And then the same for y. Right. Okay. That's 7.5 for sine. Anyone got that too?
Yeah.
And then I got 12.99 for cosine, right? All right, and so that solves for your initials on the both x. So you can add that onto your list. So for VOX, it is going to be 12.99. And VOY is going to be 7.5, right? So now we have the final velocities, right? So again, final velocity. My velocity to be. In this case, this motion ends when the ball hits the floor. Now again, there's a lot of exceptions in physics, and it will do you really good to know these exceptions, because if you do, it will save you a lot of heartache, right? And the exception comes with this. Formulas, and they will not give you correct answers. They'll give you an answer, but it will be wrong. So it has to be something above or below 0, right? That makes sense? So here we have initial velocities, so we can assume our final velocity to be 0. And then all that's left is our x and our time. All right, x on the displacement on the x, displacement on the y, and our time. What's up?
In the x-axis, isn't
It would be the same thing if you want to look at it that way. Just know that, again, there's no acceleration in the horizontal axis. So essentially, it breaks down to the same thing. I just like, but if you like to look at it as it's constant the whole time, x over t equals v, like the very simple formula on the horizontal, remember? So we don't need an initial and a final. So, all right, so now we can plug and chug our y to solve for time, and then we can go for displacement, right? So I'm just gonna, do you guys need me to have like the kinematic formulas in the corner, or are you good because you have them written down? Okay. So I'll just have them kind of like that, just in case. All right, so we can go for v final equals v initial plus a t, right? And so 0 is equal to 7.5 plus negative 9.8, 7.5. All right. Did you get the calculation for time? Yep. 0.7? All right. 0.8 then. All right, so now, again, 0.8 is time, and time is the only variable that can go on both axes, so we'll fill them in for both, right? And remember, it's an acceleration of 0, so we can use these easy formulas right here. And so we can solve for displacement just by doing the velocity times time. So the velocity on the x-axis is 12.99 times the time of 0.8 seconds, and that will give us our x. And so that gives us a displacement of 10.392 meters. All right? And now we can plug into this formula, the x equals VOT, to solve for the x on the y, right? And so we're going to get x is equal to 7.5 times 0.8 plus 1/2 negative 9.8 times 0.8. Anybody solved that yet? What did you say, Shannon? So 2.9. So remember, x's and understand. Right? All right, so that's the problem, and now we go on to the conceptual stuff, right? So 2D kinematics are also dictated and known as projectiles, right? So a good way of looking at a projectile is by graphing it, as always. And we're going to notice some really interesting projectiles, and that's that they make parabolas, right? If you have, so as you have the motion, it's going to go up, and it's going to go back down. And the neat thing about parabolas is that they're symmetrical, right? Out when dealing with parabolas associated with free fall and things like that. If we look at this parabola, we know that the time to take to get to the top, right here, we're going to dictate that as time 1. And then the time to get to the bottom here is going to be dictated as time 2. And if we look at the relationship between time 1 and time 2, we realize that they're equal. It takes exactly the same amount of time to reach the maximum height as it does to fall back down. And so what you use this for is, remember how I said that your kinematic formulas do not work, plug in 0 for both the final and initial velocity? This is how you get around that. What you can do is you can assume the final to be 0 and the initial to be whatever it is, and solve for 1/2 of that parabola, and whatever you get, you just double it to get the full projection of the motion. Because we know time 1 and 2. And whenever you plug in a velocity final as 0, you're solving for this maximum height point. So that said, we can now look at the velocity at each given position, right? So here, at this point right here, can you guys see that dot? Like, is it clear enough on there? Yeah. You've been kicked, and you have a vertical component of velocity and a horizontal component of velocity, right? So now we can follow this along the projection of the motion, and we can learn things about its kinematics. So here, the horizontal velocity will remain constant, right? Because acceleration acting on the horizontal, and these axes are independent. But there is an acceleration, and that's gravity, and we can expect that to negatively impact the velocity, so it decreases, right? And then at the top, you have a null acceleration of this motion, and all that remains is the horizontal velocity. Now at this point, acceleration is now acting on our object, gaining a negative velocity, while horizontal, as always, remains the same. And then the moment right before it hits, it will have the maximum negative velocity with the same constant horizontal velocity. So what Tesla to do as far a very good chance you're going to see on the test is that these individual points will be labeled with letters, like so, and then multiple choices. I might say things like this, like the vertical velocity at B is equal in magnitude of the vertical velocity at D. Now, you have to be really careful with definition. Does magnitude involve direction? About the magnitude at points B and D, that vertical so with that graph, usually how the concepts will be handled. All right, moving on. So now we have forces, right? And so of course, you guys know Newton's 3 laws. And by memorizing them, just know how they apply to math and how they affect your conception of things, right? So the most important formula would be force equals mass times acceleration, according to Newton's second law. So that is an important formula to know, right? Force equals mass times acceleration. The same thing can be said if you're looking at a net force, right? Is going to be equal to the mass times its net acceleration, right? And in essence, what this breaks down to is the net force will always be equal to the winning force minus the losing force. And the way you know acceleration is pointing in the same direction as that force, right? Coming the other force, and it's applying enough additional force that it's causing your object to accelerate. All right, so the first type of problems you're probably going to experience as long as forces are force diagrams, right? And those are simple, they're very important to know. And even though a question might ask you to do a force diagram, I would still draw a force diagram because they're very good. They act as like checklists to know, am I including every force and am I using all the formulas correctly, right? So your force diagram would have your object as the dot, and then all the forces applied to it. Usually, depending on the situation, they like to ask questions like, when you're sitting in a car and it's going at a constant 30 meters per second, right? So let me draw that to the side. So you, excuse my poor drawing, that's going to be our car, and you are in the chair sitting, right? And they want you to, and this car is traveling at a constant 30 meters per second. They want you to So a lot of people saw a force here as the car is pushing on the kid, keeping him going forward. There's a thing you guys need to understand in physics is about changes and things. So if you start where you end, essentially in the eyes of physicists, we don't care. It will not matter. It's not going to be reflected in math in any way. And so that's what's happening here. Though you're going through a constant velocity, your acceleration is 0 because you're not speeding up or slowing down. So as far as the x-axis is concerned, your forces are either equal or you're just not going to write them at all. So unless it include every force, this force does not count. The only force that you're actually experiencing is the normal force that is placed on the chair that's keeping you from sinking through the chair, and then the force of gravity that's preventing you from flying off into space. So you guys see it does not, so we're not assume there's force in the direction of velocity. No, it depends. It's all about, right? So if they asked you the perspective of the car, then there would be, but there would also be the applied force of the car's engine pushing the car forward, right? Looking at the boy sitting in the car, he's not rubbing against the seat as far as we know, so there is no, he's not moving on the x-axis. All right. All right, so now how forces are applied. So, all right, so again, a big thing to know about forces is how to solve for the different forces and what they mean, right? So again, we have the force of gravity, which is simply your mass times g, the acceleration due to gravity here on Earth, right? Then we have normal force, right? Which is going to be equal to Fg with the asterisk, right? Normal force is the force that a surface applies in response to your force of gravity. So as you're weighing down the floor pushes back an equal amount, right? Every action has an equal and opposite reaction. But vectors do matter, and so does direction. So if you're standing on an inclined surface, right? An inclined surface, you're pushing down this straight force, right? But because of the theta and the incline of the surface, this actually divides out into component forces, right? And because of that, your normal force can only respond perpendicular to the angle of your surface, right? So that's why we can't just say Fn is always equal to Fg. Fn is equal to Fg if the surface is horizontal. But if there is a theta involved, we now have components, and Fn will be equal to mg, the force of gravity, times cosine theta, which is the correct component that you're applying onto that surface. All right? Now we have the force of friction, which on a horizontal surface, because this one is also dependent on the direction of the surface, would just simply be normal force, or mg, right, times mu, right? But as we talked about with normal force is dependent on the theta involved on the surface. So if there's a theta involved, force of friction will end up being mg sine theta times d mu, which is the coefficient of friction. Right? Now, a good thing to understand, you might not always be asked to solve for it, very unlikely, but it's good to understand what this coefficient of friction means, right? The coefficient of friction is simply the ratio of forces involved in the force it takes to lift an object divided by the force it takes to push an object. Actually, no, my bad, guys, sorry. Flip that. It's the other way around. It's the force to push over the force to lift. All right? And so that's why a question might ask you, why is it very rare that a coefficient of friction will be above 1? Right? Because if it's above 1, that means it is harder to push the object than it is to, or my bad, it is harder to lift the object than it is to push the object. And think about it. Does that make sense in your head? That usually when you think about something that's really heavy, do you want to lift it or do you want to push it? Yeah, exactly. You want to push it because it tends to be easier. But on surfaces that are not very often, there are some surfaces where you actually have to push harder than you would have to lift. And that doesn't happen very often in nature, and that's why coefficient of friction is usually below 1, because it's usually always easier to push something than lift something. All right? So that said, a good way, they might do this with the amount of push and the amount of force it takes to lift. So you divide the two to solve for a coefficient of friction, right? And the last thing about coefficient of friction is that there's two of them, right? There's kinetic and there's the static. When you have an object at rest, it's usually to start it to move, then you would have to push to keep it moving. Usually, the static coefficient of friction will always be greater than the kinetic coefficient of friction. And so you use kinetic coefficient of friction when an object's already in motion. And you use the static coefficient of friction when it's at rest. Make sense? All right. So I kind of already introduced it with the components of as far as friction and normal force, but forces on inclined planes, right? And this one will trick people up because flip the axis the right way. And so a lot of people will see, all right, so we have a block here, right? Just pretend that's actually a properly drawn block, right? And so it is sliding down and it has an acceleration downwards. And so so we have to draw a force diagram, and so we know that there's this downward force of gravity. We know that perpendicular to the surface is the normal force. Resisting motion is the force of friction. And then you have the applied force, which is going to be a component of gravity, right? Because pulling down this block down the surface is gravity. Right? And so this one is known as the FGY, or at least I like it that way so I don't get it. Because students like to think that the counteracting force to normal force, since normal force is actually pointing up towards the sky, would be Y, but that's wrong. Because if you think about it that way, you're going to get your trigonometric functions backwards. Remember how at the beginning of the session I said cosine is always with x and sine is always with y? Well, if you do it this way, it's actually the other way around. And this is the exception I was talking about, where sine goes with x, because to solve for this applied force of the x-axis, that is that would be the mg sine theta, right? That's going to be, and so that's why I like to write it as FGY, so I remind myself, hey, this is using sine, not cosine. Now, if we look at it, FGY and the force of friction, you guys can't see that. Force of friction and FGY have similar formulas. And you would think friction is going to be bigger, and it won't, because remember that the coefficient of friction is usually less than 1. So you're multiplying by a decimal, which reduces the overall number. The only time it's going to be bigger is if the acceleration here is pointing in the opposite direction. And so we can break this down into our net forces, saying the force winning, which is the force that has the same direction as acceleration, which would be FGY, minus the force losing, which would be the force in the exact opposite direction of A, which in this case is the force of friction, is going to be equal to the net force. Everybody get that so far? Because now we're going to start plugging and chugging, and it might get a little confusing. So if you guys get lost, don't be afraid to holler and stop and explain it, because now this is kind of crucial as far as the inclined planes and understanding where these formulas are coming from. All right, so we have that this net force is going to be equal to the force of gravity minus the force of friction, right? So now we have to start replacing variables. So we know that the net force is going to be equal to the mass times the net acceleration experienced by the block, which is this net acceleration here is the same A as this arrow over here. And that's going to be equal to the quantity of mg sine theta, right? Because that's the force of gravity, minus the quantity of mg sine theta, cosine theta. Cosine theta times the coefficient of friction. Make sense so far? Right. The reason we're using cosine theta, right, is because the force of friction, right, the force of friction also has another formula that relates it to normal force, right? That I wrote up here. That normal force, all right, force of friction, oh, I actually didn't write it. Excuse me, guys. Sorry. So force of friction is equal to the normal force times mu, right? Right? So that normal force times mu, this will break down to the component for normal force, which is mg cosine theta times mu, and that's how we get that. Everybody has that written down so we can actually put numbers to this? All right. So, alrighty. All right, so now we're going to have the same inclined plane. With a box that weighs 15 kilograms. And just for the sake of easy math, we're going to assume that g is equal to 10, not 9.8. It's just rounding up. Right? And so we know, and we're going to say that the coefficient of friction is equal to 0.2. So this, oh, what's up?
For the coefficient of friction, should we, for static kinetic, let's just depend on whether or not they say it's like
Yeah. 9 out of 10 times, if they only give you 1, it's usually just use that 1. The only times they give you 2 is usually in a series of problems where you have to solve for it and in motion. And so it usually is 2 to 3 multiple choice questions. It might be like on the test, it might say, use this following diagram for questions 3 to 6. And then they'll give you 2 coefficients of friction because it's multiple questions. At this level of physics, you're not going to be using both in one formula. All right? All right. So this question would probably look something like they'll give you this diagram. Kids, read that properly. That's 15, just to clarify. And then say, draw a force diagram and solve for the extension that this box goes down. Like how fast is it going down the incline, right? And so we start by drawing the force diagram, right? And so,
We need angle.
yeah, true. Good catch. Theta will be 23 degrees. Let's do that. Just did. Gotta keep you on your toes, Chandler. Right? And so we experience the force of gravity, the normal force, and then the force of friction, then the component force of gravity, FGY, that pulls it down, and then the component responding force of normal force, which we're going to label FGX. So that would be your force diagram. So remember these are also vectors, forces are vectors, so we're only going to deal with things that are directly in line or perpendicular to each other. So that's how we're going to approach this. So we know, so let's start solving for our variables. So we know that Fg is just simply going to be the mass, 15 kilograms, times the gravity 10, which is 150 newtons. Right? Now the force normal is going to be equal to the component force of gravity, Fgx, because remember that if forces are equal, the acceleration is 0, right? And so we know that this block is on this surface, and it's not sinking through the surface, bouncing off, right? So on this axis, axis right here, we know that acceleration is 0. Does that make sense how we come to that conclusion? And since we know that's 0, we can also assume that these two opposing forces, FGX and Fn, are equal. And so we know that FGX is equal to mg cosine theta. So we just do 15 times 10 times cosine 23 degrees. 138? All right, so 138 newtons. And now we can also solve for the force of friction, because we know force of friction is Fn times the coefficient of friction. So Fn we just solved to be 138 newtons, times that by our 0.2. All right, 27.6 newtons. And all that's left now is FGY. FGY, which we know is equal to mg sine theta, which is going to be 15 times 10 times sine 23 degrees. Got an answer for that one?
Yeah, it's 58.6.
All right, 58.6. All righty. And now we can just start adding these labels, right? So we know FGY is 58.6 newtons, and we know that this is, F force of friction is 27.6 newtons, right? So now we can identify which way acceleration is facing. The force winning minus force losing, we know 58.6 is bigger than 27.6, so acceleration is pointing down the slope. Now let me ask you guys this question. If the force of friction in this case was greater than the force pulling the block down the hill, would acceleration be pointed in the opposite direction? Why? Yeah, exactly. Force of friction is a non-conservative force. Force of friction isn't actually applying a force in the opposite direction. It's only applying a resistance. So that resistance has a quota, which we saw using the formula. So greater than that quota, we'll experience acceleration in the opposite direction and overcome friction. Anything that's below that quota that we saw by force of friction simply just won't move. Because think about it. Force of friction is the experience that stops us from moving when we drag something across the surface. Does it make sense that same dragging would push us in the opposite direction? It would just stop us from moving. So that's also another concept that could be asked conceptually to understand that friction is resistance. It's not an actual force in the opposite direction. It's non-conservative. All right, so now to solve for our acceleration, how that's equal to. All right. So we know that the net force is equal to force winning minus force losing. And we know force winning in this case is 58.6 newtons minus 27.6 newtons. So we can solve that to be 58.6 minus 27.6 to be 31 newtons, right? But we also know that the net force, that the net force is equal to mass times acceleration, the net acceleration. And we know that if net force is equal to 31 and our mass is equal to 15 kilograms, and it leaves us A, so 31 divided by 15 will give us our acceleration of 2.1 meters per second squared. And that's how you work that problem out. Alrighty. Okay, so I don't have enough time to work out a full another problem before I wanted to give you guys a break. So we're going to take a 5-minute break. You guys can bathroom break, water, And we'll probably start at 310. No.
SI that you can figure out the profile.
Yeah.
I went to the other SI session and figured it out.
Really?
Yeah. Do you want
Yeah, let me see that.
let me see if I can find it in here. Otherwise, I have a picture of it. I just took pictures of it. I didn't actually write it. So. I'll pull it up on my computer. Is this question?
Yeah.
Yeah.
Hmm.
Were you wrong earlier?
When?
You said force of friction was under the side.
Yeah. Yeah, that's wrong. Yeah. I got confused. I was going fast. I'll make when everybody's back from break. I'll like point it out. But like I myself left.
I noticed
Yeah.
and then I was like, wait.
Yeah. Okay. So yeah. Okay, so you just assume. Oh, okay. Yeah. Okay, I see what they did there. Yeah. You just set it up as a system of equations. Okay.
I just remember you stuck on
Yeah.
But the other,
Yeah. Yeah. That's what I thought.
he says that it'll probably be on the exam though, and then they'll just give you tools.
Yeah. I mean, that way it's easy. It's just like the kinetic problem. Tomorrow I have Bio 2, Chem 2, and Neurobiology. But then as soon as I finish all my testing tomorrow, I'm done. So I'm done the first day of finals, but it's rough. It's like, yikes. Yeah. Who do you have, Hampton or? Oh, okay. I mean, it's an ACS, so everybody's taking the exam. Have you seen any of the ACS like study guide things?
Yeah.
So, it doesn't look too bad. It's very like conceptual. Yeah. Calculus is Saturday.
Neuropsych.
Not bad.
It's actually pretty good. I think next is going to be a little bit more difficult. By the way, I was going to sign up for the neurobio, but then I switched to social psych. But like, do you think it's
Here's the thing: is like if you're a type of learner who needs like consistent lectures and things like that, it's going to be rough. But if you're the type of person who's good at working with the yourself, it's a fairly easy class. Yeah, so it just kind of turns out to be, because it's like half online, half like about them is that the PowerPoints, that's all. Yeah.
It's kind of how remote classes right now.
Yeah.
Where it's like
So.
physics classroom is like where you learn.
Yeah.
But I don't know. I had originally signed up for it, but then I talked to my advisor, and she's like, no, you can use your class. And it would be, I'm already taking 3 labs: the
Yeah.
chemistry lab, physics lab, and anatomy lab.
Yikes.
Yeah.
That'll be fine.
So I'm
Just
basically taking like 7 classes.
fun. All right. All right. Let me mark off what I've done so far. Alrighty. What's up, Henry? And Ramon? Yeah, I don't think you guys really got to it, but I know the other professors did, so I'm gonna like brush it over. It's not too complex. It just pretty much works out to like plugging and chugging, and you get the formula sheet. All the moments of inertia are calculated for you because they're calculus derived, so you get those, and it's just like a matter of using them.
So, is it okay if I leave a little bit early?
Yeah, that's fine. You don't have to stay the entire time. People have been coming in and leaving as they feel.
I'm
So
just going to another study session.
yeah, I feel.
Yeah, I'm going to study that, but there's a chemistry one that I'm gonna go to, but that's like
Yeah, I solved that one. You do use you have to use kind of both in a way. I was actually going to do this problem, like where you see forces plus kinematics. It's like this type of problem. It's actually like one of the first problems I'm going to start off like now. Alrighty, guys. We're going to start up in a second here.
her name is Nicole. I never remember how to spell it. It's like 13 letters. Yeah, something like that. She's really nice. She just got her PhD. She's in the middle of her PhD. I feel so bad for her. She's doing research. She's teaching here. She's taking classes, and she's teaching at something.
Yikes. Alright, guys, let's bring it back in. I'm going to start up. It's a little early, but. Alright, so for the most part, we've hit a good majority point. We're like on the last overall unit. So all that's left to do is combining kinematics and forces, energy, and then rotational and some moments of inertia stuff. Depending on your professor, it's different, because I know the Raman guys haven't really even touched inertia and statics and things like that, while others have. So we're just going to do a brief overview over that stuff, because though it's important, it usually just turns into simple one-to-one plug and chug. So I'm going to get, so these, probably the end, it's going to be a little more simpler stuff. But right now we're going to hit more of the hard-hitting, longer problems. So let's get right into that. All right, so forces and kinematics. So as we know, forces and relate terms like and newtons back into acceleration, right? And we can solve for overall different kinematic features that we need to know. So it usually turns out into the more simple things. So how did that work? Okay, so we have an inclined plane, right? So we have a box that's pushed down the inclined plane, right? And it goes all the way down the inclined plane, and it travels a distance of d. And we have to solve for d. So here's what we know about this box. This box is 10 kilograms. The incline itself is frictionless. There's no friction to account for. And is there anything else on that problem, Henry? Like, I'm changing the numbers because I'm not.
2.2 for
Okay, so it gives you a kinetic coefficient.
and the degree.
Yeah, so we're going to have our kinetic coefficient of friction be 0.15 and our theta be 30 degrees. So that's what we know. So as we go down this incline, we need to keep in mind the force diagram and what we're actually relating, right? So Again, we have the normal force that pushes against it, the force of gravity, then the component of gravity that pulls it down the incline, and we can ignore friction because the problem says that it's on this point. So the overall battle plan of this question is we solve for the acceleration. Also, I forgot to tell you that this incline is 15 meters. It gives you the distance of the incline. Yeah, the incline. So the hypotenuse of this triangle is 15 meters. So this part. So we find the acceleration, we calculate its final speed, and then we use that final speed as speed and how far it goes from there. So in essence, this is actually two problems in one that we can divide upon this axis, right? So we know that FGY is the winning force because it's the only force. So we can calculate that using mg sine theta. And again, we're going to have g be 10 just for easy math. So we have 15 times 10 times sine 30 degrees. All right, so 75 newtons. So that's our net force. So we know a net force is going to be equal to a mass times an acceleration. So we can do that. So 75 divided by our mass of 10 equals 7.5 meters per second squared. So acceleration that we gained going through this incline. So now we can treat it as a kinematic problem and solve for things we need to know. So this represents the division of the problems because, like I said, it's two problems in one. So right now we're working on this first problem right here. So now that we have the acceleration for this first part, we know it's 7.5 meters per second squared. We know the initial velocity is 0 meters per second because it starts from rest. The displacement is given to us as 15 meters. And now we just have to find the final velocity, right? And so why do we have to find the final velocity for this first part? Exactly, because as it follows, nothing, though we're dividing this into two problems, we have to imagine that it hits its final velocity here, and it keeps going. So the final velocity for this first part is actually the initial velocity for the second part. So we can calculate the final velocity using v final squared equals v initial squared plus 2ax. So we have the final velocity is what we're trying to find. Initial velocity gets zeroed out because we start from rest. And so we have 2 times the acceleration of 7.5 times the displacement of 15 meters. And so will give us a final velocity. Remember that this is still squared, so we have to square root this to give us our final velocity. So that will give us 15 times 7.5 times 2. I think it gives us 15.
Yeah.
So that gives us a final velocity of 15 meters per second. Yeah, sorry. Right? And so now, velocity is the part. So we're going to start a new bracket. So I'm just going to draw the line here, right? So this was the first part. So our new bracket is our initial velocity being 15 meters per second. Our acceleration, we don't know. Use forces again to calculate for the acceleration of the second part. Because the second part, incline was frictionless, second part isn't. We have a coefficient of friction of 0.15. So we know that the force of friction, sorry it's getting sloppy here guys, The force of friction is equal to the normal force times mu. And so the normal force is going to be mg cosine theta times the mu. Right? So we get 10 times 10 actually, okay. 10 times 10, right, because the mass is 10. Oh, wait, quick edit, guys. I think for the first part, I accidentally put 15 as the mass. Instead of, yeah. Guys, if I do these things, you got to catch me up. I got that dyslexia, dudes. It should be, remember, the formula is mg sine theta. M, not 15. Yeah. I was testing you guys. You all, no, I'm just messing with you. So yeah. So if one of you wants to rework that math while I keep moving on.
Can you just change the mass to 15 now since we're already getting full math for it? Or?
Well, he already saw for it. All right, so it's 12.3. Scratch that. This is 12.3. 12.3. 12.3. I'm just going to scratch that out, put a little 10. There we go. Good as new. Yeah, and the acceleration change. What did you solve for your acceleration?
5.
Yeah, 5. All right. Back on track.
This is 5.
Yeah.
50.
Yeah, so this is 50. Whatever, just so the notes are. All right, so then we have 10, 10, cosine 30. Did anyone solve that? All right, 17.3. Is that with mu multiplier? Okay. So I'm just going to 0.15. All right, so that's our net, and so we do 17.3 divided by the mass 10 will give us our our negative acceleration, right? Because this is in the negative direction. The force is opposing our motion, so that's why we put negative. And so we get 1.73 meters per second squared. And so now we have an acceleration of 1.73 meters per second squared. That's negative. Our final velocity is 0 because we're going to stop. And we need to solve for x. And so the formula v final squared equals v initial squared plus 2ax. So 0 is equal to 12.3 squared plus 2 times negative 1.73 times x. Negative 12.3 squared divided by the product of 2 times 1.73 will give us a displacement. 43.7. And so that is how far the box will travel after coming up that incline. And speaking of mistakes, I correct myself like low-key in the old notes, but if you guys have been writing everything I've been saying, I have a contradiction in the notes. I accidentally put in the first part that the force of friction is mg sine theta, and then later I said force of friction is mg cosine theta. Cosine theta is correct, so scratch out sine theta if you have it in your notes. Yeah. Okay. And so that is how forces and kinematics will come together. So you can expect problems along those lines. Okay? Now to energy. Alrighty. So the thing you guys need to understand about energy and the actual approach to how we solve energy problems is that energy is conserved in our systems, right? So if you can find a point where all the energy is in the same state in a problem, that gives you a maximum energy, and from then on, you're only So, for example, like we have our types of energy, right? So we have potential energy, which is equal to mgh. We have elastic potential energy, or spring potential energy, which comes out to 1/2 k, which is the spring constant, times delta x squared. And delta x is how far the spring is stretched or compressed from equilibrium. Then we have kinetic energy, which is equal to 1/2 mass velocity squared. Right? And so you can find a situation in a problem where energy is all in one state, be it kinetic, potential, or spring. That gives you your total. And from there, you can create the other forms of energy that are present throughout the problem so that solve for any action, right? So I'm actually going to jump off with because we're running out of time, so I want you to see more of the harder problems and the easier problems. Of a harder problem that also introduces rotational kinetics into it. So as we go through, I'm going to be throwing formulas that are from rotational kinetics. And if you're lost, just raise your hand and I will explain where that formula comes from and what it's used to surmise, right? So we have another hill, and we're asked to solve for the height of this hill, because this hill is the ramp an ice skater used to perform a stunt acrobatic. So what this ice skater is going to do is he's going to start at this top of the hill, and he's going to skate down, picking up speed, much like the box problem we just solved. And he's going to go, and he's going to do a sick loop-de-loop. And we need to solve for how high, because it's our job to make the ramp. We need to solve how high does this ramp need to be for him to safely make it across this loop-de-loop, right? And so here's where the rotational kinetics comes apart. So rotational kinetics, in nature, things only move in straight lines, right? But we know that's not true because we can make curves and things like that. But actually, things will never curve. They only curve due to external forces, right? So as you have a velocity pointing in one direction, if you have an acceleration that's perpendicular or centripetal to it, it will cause a curve. So here, we have a velocity here, and then the acceleration due to gravity pointing downwards, right? And so that's what causes this curve. All for the minimum velocity, because we know this gravity is 10, right? Acceleration due to gravity, right? So to solve the ratio for the needed velocity that matches the acceleration to make this curve possible, we have the formula that centripetal acceleration, which is the acceleration towards the center of a circle, is equal to the velocity squared divided by radius. So, right? So we need to solve for this velocity here to be a minimum enough to the point where it matches the acceleration due to gravity. And just for easy math, we're going to say that this radius is, let's say, 5 meters, right? Right? So what we do is we know the centripetal acceleration is 10 v squared divided by 5, right? So we do 50, square root of 50 is going to equal v. Thank you, Chandler, 7.1 meters per second. So that's the minimum velocity we need to make it safely across the slope. So, but we don't have control of his speed. We only have control of it indirectly by how much potential energy. And we can determine that by the height of the ramp. So first, we can solve for the kinetic energy needed by using the speed. So if we know this man's mass, conveniently placed at 20 kilograms, super light, We know that kinetic energy is going to be equal to 1/2 mass velocity squared, right? And we know that when he is in motion going across this loop, all of his energy is in use. So it's being used, and so we know the maximum amount of energy is placed kinetically. So we can just say that 1/2 his mass of 20 kilograms times the velocity 7.1 squared will give us the total energy in this system. And so we can find the for 10 times 7.1 it is. $504.1 joules. I mean, let's just go for 4 because that's what I got here, right? And so we know the total energy in this system is 504.1 joules. And so we can equate that to potential energy, which is what we have direct control over, is equal to the mass times gravity times height. And we know that his mass is 20 kilograms, the height is 10, or not the height, the gravity is 10 h. And so we do 504.1 divided by 200 is going to give us our height. And so what is, yeah.
Because I still had my number left in the calculator when I squared it to 50, so it gave me.
Yeah, that's fine. Let's just say it's 2.5. Just for the sake of people with the notes, it comes out to 2.52.
Okay.
So that's how high we need to make the ramp, and that's how you solve that one. Yeah. I know I threw you guys in for a loop with the rotational kinetics, but you can see how we solved for the maximum amount of energy in a system, and then we equated it to what we needed to solve. Okay? Yeah. Yeah, that question, that form of question, I got it from Ramon's worksheet. At the time, she hadn't taught rotational kinetics, so that's why I'm going over it now, because she is the head of the department, so we could see a question like that. Yeah, so that's why I chose it.
So what are the equations that we need to know for?
All right, rotational kinetic, the big one is that, let me pull it down, is centripetal acceleration is equal to velocity squared divided by right? Also, you need to know that rotational kinetics is very much like linear kinetics, like where all that changes is instead of using a straight linear distance as a measurement, you're using a measurement of a curved surface, which in this case is radians, degrees. You're using that instead of a displacement in a straight line, which would be meters. So if you see here, we have our kinetic equations, right? I'm going to show you the rotational version of them. And so the rotational version just breaks to be the same exact formulas, just with replaced things. So theta, which is the percentage of an angle covered in a circle, right? So this is the angle, but this is the angle, which is equivalent to the linear formula of x, displacement. So theta is your displacement in rotational. Have omega w, which is your equivalent of velocity. Omega is just equal to radians per second. Then you have alpha, which is alpha a, acceleration, is the equivalent to acceleration, but in rotational, which would be radians per second squared, right? So that makes sense, like one. So if we look at the formulas, we have x equals VOT plus 1/2 acceleration times squared. This just converts straight over. Theta is equal to omega initial times plus 1/2 alpha times squared. You guys see how that converts over? And so the only difference between these two is that a velocity, if you have velocity, you divide by the radius of the circle, and that will give you the omega. Or if you're given degrees, you must convert it into radians, right? So, and all the formulas are one-to-one like that. So if we look at another one in linear kinematics, v final equals v initial plus acceleration times, it just works out to omega final equals omega initial plus alpha time. You guys see how they're one? All right. And so a lot of these questions will just work out to being, they'll give you a combination between linear numbers and rotational numbers, circular numbers, and they'll ask you to solve for something. So all you have to do, convert the rotational stuff to linear or the linear stuff to rotational, and then just apply it to kinematics like we worked on with kinematics before, right? So that's how that works out. And the reason I'm just glossing over that is because it's very similar to stuff we've already covered, and plus it's not that big of a chunk. I'm pretty sure in Raman you guys didn't even touch it. My point proven exactly. So we're going to move on. All right, so next is something that is fairly easy, but very important, and it's momentum, right? So momentum and impulse break down to be simply, momentum is p, and that's just simply equal to mass times velocity, right? So the more massive something is and the faster it's going, the more momentum it has, which makes sense. A truck going super fast is pretty hard to stop. And so you can always equate these things by saying that m1 v1 will be equal to m2 v2. So you can compare it to after situations. Then also we have impulse, which is equal to the change in momentum. And the change in momentum is also equal to force times the change in time. So all of those are equivalent. And so I get really good at understanding that because there will be times where they'll give you chunk pieces of one and you use it to solve for other things. So I'm going to do one math problem and then one conceptual problem. And then I'm going to briefly cover inertia and statics, and that should be good, all right? So this is a really popular momentum question. And so we have two football players, right? One weighs 100 kilograms, and one weighs 60 kilograms. But he is going 15 meters per second, while he's going 5 meters per second, right? And so this question can ask a multitude of things. It can ask which direction will they collide. And so to know about collisions, which is the most oftenly asked question in momentum, there are two types of collisions. Inelastic, inelastic, which means the two objects that collide stick together. So you have two objects that become one object. Or elastic objects, where they bounce off of each other, where two objects remain two objects after the collision. In this case, it's a football game, so you're going to expect the big guy to try to stop the running back or whatever it is. So this is our before, our initial. And so our after is going to look something along the lines of this. Right? Now it's our job to find which direction that's going and how fast. So we can solve this by solving for their momentums. So the momentum of the smaller guy is just going to be 60 times 15. Which comes out to 900. While his momentum comes out to be 500, right? And since these are also vectors, you need to take in consideration the direction. So this is negative 500 because he's going in the opposite direction of the other one. So their total momentum together is going to be 400, right? So now their new mass, because they're now together, they have collided and become one. We're just going to add their masses, 160 kilograms. And then to find their velocity, we just do momentum divided by mass, which will give us the velocity. So 400 divided by 160, which comes out to 2.5 meters per second, and it's positive, which means their motion is in that direction. Make sense? All right, another one that is also popular to ask and very practical because we know we're all going to space one day is that you're an astronaut and your safety line back to the space station has been tethered. And so the space station is over here 50 meters away. And so this kind of uses Newton's law. Every action has an equal and opposite reaction. So all you have is a water bottle. And so you decide to throw the water bottle away. And the water bottle has a mass of 0.15 kilograms. And you throw it away at a speed of 5 meters per second. And you weigh 100 kilograms. So now, how long does it take to get back to the space station after you've thrown away the water bottle, right? And because it's momentum, we know that the momentums are inverse, and so we can equate it. So if we throw the water bottle at 5 meters per second and it weighs 0.15, we can just do 5 times 0.15, which gives it a momentum of 0.75. And so since it's an elastic, the momentums are equal to each other. So our momentum as the astronaut will be 0.75. And so we can do 0.75 divided by 100, our mass, to give our speed. Our velocity would be 0.0075 meters per second. And so if we wanted to find how much time would it take to get back to the space station, we just do the distance divided by the velocity. Yeah. And so it would take 6,666 seconds. Just for convention's sake, so that would take about 111 minutes, about 2 hours. So hopefully you have enough oxygen. Also, another aspect add on oxygen you have, like they might you of alive or will you be suffocated. In this case, oxygen, unless you hold your breath about 105 minutes, I really doubt it. Yeah. All right. All right, so now it's the conceptual stuff, right? So a famous question they love to ask in physics because it's so outlandish is that you have a giant truck and a fly. And they collide, right? And they have an inelastic collision. I like to ask the force impacted on the truck versus the force impacted on the fly, the relationship between it, and the momentum, right? So a lot of people would like to say, oh, the truck has way more force than the fly, overcomes it completely, which is not the case, that they're equal and opposite. So the force impacted onto the truck is impacted onto the fly. The truck is much more massive, so it can deal with it, while the fly, not so much. We can see that, especially in like a recent news article just 2Ds came and showed it to me of a bird hitting a plane. So, important concept. Then, as far as impulse, so impulse is the change in momentum, right? And so the change in momentum in the flight, again, will be the same as in the truck. And we can also illustrate this mathematically by looking at different problems. So they like to ask this problem where you have a ball that hits a wall and bounces off, right? And so they can ask you a lot of different things. Like if I give you the force of the ball hitting this wall, I can fairly ask you, how long does the ball remain in contact with the wall, right? So if I say you have an impulse of 0.250 and a force of 15 newtons, you can tell me the delta t, remember? Because impulse is also equal to force times delta t. So we would just do 0.250 divided by 15 will give us our delta t, which should give us a time of 0.1 or just 0.2 seconds for rounding, right? I could also ask just what is the impulse if I give you a velocity number, right? If I say this velocity is equal to 2.5 meters per second to negative 2.5 meters per second, you can do final minus initial. Negative 2.5 minus 2.5 gives you a negative 5 meters per second times the mass, which let's just say is like 0.1. And you'd get a impulse of negative 0.1, right? Straightforward. All right. Would it be? I made these two numbers like independently. Like I just made, they're not equivalent. Like that's a completely different case. So don't worry about it. They're independent because I just made up the question on the spot. All right. Okie dokie. So inertia in statics, right? All right. So how statics breaks physics of maintaining rest, of what you need to do to keep things in balance so they don't move, right? So statics usually loves to ask questions along of a seesaw, right? And so for here, it's very similar to momentum. Do the force applied times the radius. And the radius in this case is only important of where the force is being applied to the fulcrum. So if I have a force applied right here, only this distance here would be considered the radius. You would ignore all of this, right? And so I like to have questions with the seesaw, right? Where you have a force applied here of 15 newtons and a force applied here of 5 newtons. And it likes to ask you, if this is 2 meters, how far is this distance here? And so you just do 15 times 2 gives you 30. And so you need 5 times a distance that would also give you 30, which we know is, again, this picture is not drawn to scale because usually if you have a small mass and it would be further along. So this would give you 6 meters. I know it doesn't really make sense in the picture, but you guys get. All right. So, all right. So also, a question could be along the lines, if this bar that's acting as our scale has a weight, right? And we have a center of gravity. So a good question that one of the worksheets had a while ago is Nitro is doing a stunt right here, and he's trying to see that there's this bar here, like so. And so, again, the force of gravity on the bar is keeping it horizontal like that, while Nitro's force here, pushing down here, is creating an opposite and equal force here. So we need to find how far can Nitro go while still being safe. So if Nitro weighs 60 kilograms, and this bar is 4 meters long, and the bar itself weighs 50 kilograms, right? And these points, this is the 0, and this is the 2.5 meter point, right? So we have to create an equation, right? So we know that a radius times nitro's weight, and the radius is what we're looking for, is how far can you walk from the center and still be safe, will be equal to the counteracting force, which is the weight of the bar times its radius. Now, you might be inclined to say the radius is 4 meters, right? But that's not the case. We're looking from the point of where the force is applied to the fulcrum. This bar is evenly distributed, right? Because it's a normal uniform bar, and we haven't been told otherwise. So we can assume that it has a center of gravity, and that is where the force is being effective mathematically. And so that center of gravity in a uniform motion, right, will be at the halfway point, which is 2 meters here. And so you want to find the center of gravity for any fulcrum and subtract the difference between them. So our fulcrum here is putting on the pressure and maintaining the seesaw effect versus the center of gravity, which is where all our force is being accumulated. And so that will give us our 50 kilograms, which is our force. Or, excuse me, this should be newtons, guys, because it's a force, not a mass. 50 newtons times the difference between the fulcrum and the center of gravity, which is 2.5 minus 2. And so you find that to be 25. And so we need 60 times a safe distance, which will give us 25. So you just do 25 divided by 60. And that will give us a radius of 0.42 meters. So nitro can walk 0.4 meters away from the fulcrum and still be safe and not have our flip on him. And that's how statics breaks down into. All right. So we have 10 minutes left. I'm going to be open here for any last thoughts, questions, if you guys have any, if you want me to look at any problems. The only things that I missed and didn't have time to cover, we've covered everything on this schedule, so if you want to take a picture so you have a note for comparison, but what I haven't would be torque. Which again is just kind of like statics, which is just a radius times a force applied, and that changes depending on the angle, which works in statics. Torque is actively maintaining, trying to open or move something. X is trying to keep it closed. So that it has a few formulas associated with it, which I'm sure you can find in PowerPoints or the textbook, but I don't have enough time to go fully in depth on it. So, is there anything you guys want to ask me about? Sorry to put you guys on the spot. You guys probably didn't think you'd get question time. All right, so that's the majority of the material. I still wouldn't use this as like a definitive study guide. I would still do past homeworks and things like that, guys, to prepare, because you may have missed them. A full semester in 2 hours. It's like, so as far as like took the physics exam, is take your time and read the questions carefully, because though it's not going to be as you think, but where you're wrong if you're not conceptual questions. They like to throw in key words that will change the meaning of draw your pictures and things like that. All right. Around you guys, there's like these little so questions or anything? I mean, I didn't go over circular motion that much because you got to understand one of the professors didn't even, so I guess so, but I went through it like